Okay, so we had introduced a general prescription for how to make a basis change from one function f, depending on x and y, to a new function g, where the differentials would be expressed via u and y. And this was done by the Legendre transformation, which was the original function minus the product of the two variables you wanted to interchange. And we'll have a look at a practical example of this. For instance, in thermodynamics. In thermodynamics, you often use a quantity known as the enthalpy, which I have here written as curly h. Usually you can write h, but I don't want to confuse it with the Hamiltonian of the system. So you often use the enthalpy in order to characterize various types of reactions, to see whether they are possible or spontaneous or not. And the enthalpy is a function of the entropy, S, of the system and the pressure, P. Now, if you know the enthalpy of the system, you can obtain the temperature by partially deriving it with respect to the entropy, and you can obtain the volume of the system if you perform a partial derivation of H with respect to the pressure. So an increment in H can be written like this. So you see that this holds true by replacing T with the partial derivative here, and V with a partial derivative here. The enthalpy is particularly convenient in order to characterize processes which are isentropic and isobaric. By isentropic, I mean that the process conserves the entropy. The entropy remains unchanged, whereas by isobaric, I mean that the pressure remains unchanged. And we see that if this is the case, then S is constant, P is constant, and therefore the enthalpy should also be constant. Assume instead that we're now dealing with a process or reaction which is isothermic and isobaric. So it's isothermic instead of isentropic, which means that the temperature remains the same in the process. In that case, it would be more useful to have some thermodynamic function which would be depending on T and P, since both of them would be constant in the process. And let's call this function g. Well, according to the Lagrange transformation, we now know of a way we can achieve precisely this. Namely, we take the original enthalpy of the system and subtract the product of the two variables we want to interchange, temperature and entropy. By doing so, one of the terms in dH will cancel with a term here, so that we're left with this. By writing G in this way, we can immediately observe that the volume will then be obtained by partially differentiating G with respect to the pressure, whereas the entropy will be obtained by a partial derivation with respect to T and an extra minus sign. So the volume, the way to obtain the volume remains the same. In that case, we derive the enthalpy with respect to P, same thing here, because we only interchange the entropy and the temperature variables. And I can mention that G is a well-known function in thermodynamics. It's actually the Gibbs free energy. Let's go back to the Lagrange versus Hamilton formalism, where we stated in the previous lecture that we want to make a variable change from Q dot, to Q and P, the two canonical variables. We know how to do this now via a Legendre transformation. So if I want to obtain a new function h with a basis q and p from a function L, which depends on q and q dot, what should my Legendre transformation look like?
L minus p times q dot?
Yes. The original function minus the product of the two variables you want to interchange. Alternatively, I can write it like this. And this is the convention. It's just an overall minus sign, so the procedure is still the same. All right, so let's see what comes out of this definition. just a chain rule for derivation. Since h depends on q, p, and t. And note that we're here using the sum convention with repeated indices. So we have implicitly here a sum over I for these terms. And let me remind you that the way you can see that this is that we have used the sum convention is that we have no I on this part of the equation, but we have I here. So in order for this equation to make sense, there has to be an implicit summation over I here. Let's now make use of this equation, or this definition, in fact, in conjunction with this one. We now make use of the definition of the canonical momentum in order to cancel two terms. If I now insert this into this term, we see that it cancels with this one. There is one more relation which is very useful for our purposes, which we may obtain from Lagrange's equations. This is Lagrange equations, just written in a slightly different form. I moved one term over so that they're equal to each other. I then use the definition of the canonical momentum here. Oh, sorry. So we get this. Let me now insert this into our expression for the differential of h. Which means that we obtain this. Now, what we've accomplished is to express the differential of h in terms of differentials of its variables, dp, dq, and dt. And the reward in doing so is that we can now identify the partial derivatives of H. And this is the central result in the Hamiltonian formalism. These are Hamilton's equations. And as announced previously, we see we have two n first-order differential equations. N equations here, n equations here, and they're first order. And what they do is that given that you know H, given that you know the Hamiltonian, the energy function of your system, you can now obtain the time derivative of both the generalized coordinates and the canonical momentum by deriving it with respect to P and Q. And this tells you how the system will evolve. So we did a lot of steps here in order to establish a bridge between the Lagrange and the Hamiltonian formalism. So let's try to summarize this in a sort of recipe. So basically this is a how to go from the Lagrange to the Hamilton formalism. By the way, one thing I forgot to mention here is that we identified these partial derivatives based on this, but we can identify one more. Namely this one. All right, so the procedure goes as follows. The first step is what you're already accustomed to, namely write down the Lagrangian of the system. Second step. Define the canonical momentum. we may now construct the Hamiltonian H, which is equal to P Q dot minus L, since we now know P, having obtained it from L. And once we have the Hamiltonian, the next step is to use the relation for the canonical momenta in order to completely eliminate Q dot. Because we want to obtain Q dot as a function of Q, P, and T, as this is what goes into the Hamiltonian. We want the Hamiltonian to be a function of Q, P, and T, and so we have to express Q dot as a function of these. And we do this via the canonical momenta here. Final step. Is then to eliminate Q dot from H. And after having done so, we are now in a position where the Hamiltonian depends on the variables we want, Q, P, and T. And by then, we're ready to actually solve Hamilton's equations. This was the formalism. This is sort of the idea behind going from the Lagrange to the Hamiltonian formalism. So we'll have a look at a couple of practical examples for how we can do so. And we'll begin with having a look at a system which is described by spherical coordinates. So we have the following coordinate system. So the generalized coordinates for our purpose assuming that there are no constraints in the system, will be r, theta, and phi, which are the three variables used to characterize any position in three-dimensional space. And let's assume, just for simplicity, that we're dealing with a potential energy that is central. So it depends only on the magnitude of the radius. All right, so we'll get cracking. We'll just write down the Lagrangian of the system to begin with. which will look like this. We have a velocity associated with the radial motion, a velocity associated with the motion characterized by this angle theta, and also the angular motion in the xy plane, which is given by this term. So we decompose the velocity into three terms. Okay, we'll just follow our recipe. Next step is to define the canonical momentum. We have 3 degrees of freedom, 3 generalized coordinates. So I goes from 1 to 3. And the first one is r. So PR, the canonical momenta associated with r, will be dl dr which upon inspection here provides us with mr dot, which seems reasonable. Next, the canonical momentum related to theta given like this. And finally, we have the canonical momentum associated with phi. All right, we have the Lagrangian, we have the canonical momenta. Next step is to write down the Hamiltonian. Where we have implicitly a summation here. So what I did now was just to write first this sum, which is the sum of all the canonical momenta with the generalized coordinate, the time derivative of the generalized coordinate, which are these terms, and then just subtract the kinetic energy and add the potential energy by using the definition of the Hamiltonian. And since we have no explicit time dependence in our problem, we know that this has to equal t plus v. So what I did now was to actually perform the fourth step and the last step in the recipe to obtain the Hamiltonian, because I exchanged or eliminated all these q dots, all the time derivatives of the generalized coordinates with their canonical momentum. So I did this by using these equations. So for instance, from the equation of the for the canonical momentum of R, I can express R dot is PR over M, which is what I put here instead of R dot squared. Similarly, I can replace theta dot with P theta over MR squared, which is what I did here, etc. So at this point, the Hamiltonian depends exactly on what we want it to depend on. It depends on the canonical momenta and the generalized coordinates, but there is no trace of any time derivative of the generalized coordinates. And by cancelling a couple of terms here, to simplify all of these fractions, I can write down this expression, the final expression for the Hamiltonian, where this is the kinetic part and this is the potential part. And a couple of things to notice here is that you have an 1 over r squared dependence for two terms in this kinetic energy. And these are the parts which are associated with momentum generated by movement in the theta direction and the phi direction. So you see that as r goes to 0, these contributions to the kinetic energy actually diverge. They become infinitely large. So for a fixed p theta and p phi, as you decrease the radius, you get an infinite amount of kinetic energy, because you would need a huge centripetal force in order to keep a particle in an orbit with a given momentum as this radius goes to 0. So this makes sense. So the bottom line here is that we've expressed the Hamiltonian as a function of q and p, where these are the variables, to be more specific. We'll have a quick look at a final example. And it's our friend, the particle in an electromagnetic field, which we've considered a couple of times by now. And as we have commented on earlier, this is actually a non-conservative system. Where the Lagrangian is written like this, with u defined here. And note that q here denotes charge and not any generalized coordinate. And with this U, we have proven that Lagrange's equations in this form, their usual form, are satisfied. And I'm using here Cartesian coordinates in this case. Okay, we'll just go through the steps again. 1, write down the Lagrangian. So note that these potentials, the scalar potential and the vector potential, which both provide the electric and the magnetic field, they may depend on both position and time. All right, let's write down the canonical momenta. Which may be derived from this form. And we actually did this, I think, a couple of lectures ago. We wrote down the canonical momentum for precisely this situation. So we see here that the canonical momentum is different from the mechanical momentum. Okay, now we construct the Hamiltonian. This is the Lagrangian up here, just written in terms of a sum convention. So we see that these terms with A actually cancel. So the Hamiltonian becomes the kinetic plus the potential energy. So this is the potential energy, in contrast to U, which is not the potential energy of the system. But we have one more step we have to perform, namely we want to eliminate all of the time derivatives of the generalized coordinates, and we want to eliminate them in favor of the canonical momenta. And we get this, where now Pi is the canonical momentum. So we see here that we have an inner product of the component of two vectors, namely P vector minus QA vector. So this can be written as So that's the Hamiltonian for a particle in an electromagnetic field. So just be aware of the fact that this is not the mechanical momentum. This is the canonical momentum. So whenever you see the Hamiltonian for a particle in an electromagnetic field, keep in mind that this is the canonical momentum, which is different from the mechanical. We could write this as follows. So it's P minus QA, which is the mechanical momentum. So that concludes the sort of transition from the Lagrange into the Hamiltonian formalism. And we consider two specific examples of how this can be done. All right, great. See you next time.